had two equilibrium points, and I did the analysis for the simple one, which was this one. So S star I star is equal to tau 0. And I gave you a bunch of eigenvalues, and basically I said that this point is a saddle if beta is greater than V over. So that's why I left you last time. And then I said we will do the second equilibrium point today, which is a nightmare, as you're about to find out. So, equilibrium point 2. Sorry. Did I do something? Because he doesn't come to class.
Not me.
Okay. So I had the other equilibrium point. My notes are. So the second equilibrium point was S star I star is equal to once again this V over beta factor mu tau minus V over B divided by V plus. And now I want to find the eigenvalues associated with this equilibrium point. So I'll give you a starting point. The Jacobian, as you can confirm, associated is IB minus mu minus S beta minus mu, I beta, and minus B plus S beta. So that's the general Jacobian we have for any equilibrium. And now I want you to substitute S and I into here and give me the eigenvalues. Do it. Go ahead. You have 30 seconds. In fact, there will be a timed portion on your exam where the TAs will sit with a stopwatch, like a very heavy chess match or something. Okay, well, I actually computed them, so let me show you them. But remember, we care about eigenvalues because I want to analyze the signs of them. So let's see what happens. So lambda 1 is equal to the following. Minus mu squared minus beta mu tau plus mu times square root of 4b cubed plus 8b squared mu plus mu cubed minus 4b squared beta tau minus 8b beta tau. Sorry? There's more. I'm not even done the square root as yet. No, it's a very nice example. Minus 8b mu tau. Plus b squared mu tau. So this is all under the square root. And then this whole eigenvalue is divided by 2b plus mu. So that's one eigenvalue. I will help you with the other eigenvalue because it's just plus or minus. So they're conjugated. So now I want you to tell me for which values of mu, tau, and beta and b is this positive, negative, or zero? Go ahead. No, I really want you to do it. Can you do it? You can do it, it's possible. But we don't want to do this. That's why I want to do this. So, it is possible, if you have a copy of Mathematica in your brain, to analyze the signs of this. In terms of signs. So, in other words, to determine this stability, but it's a nightmare, as you can see. And this often happens. See, and this is the point I made last class to a bunch of you. The dimension of the dynamical system is not a problem, whether it's 3 dimensions, 4 dimensions. It's how many free parameters you have that give you the issue. So because the eigenvalues become extremely complicated, and determine their stability, determine their size, becomes a very arduous process. So, what do? Do we just stop then?
We use simplified.
We use simplified function? This is using the simplified
Are you
function.
serious?
Yes. So it was not simplified. This is after using simplified function.
I give up.
So, do we just stop? No, we cannot do it. So for 2 by 2 systems, there's a bit of a trick actually. And let me explain it. But this trick I'm about to show you only works for 2 by 2. So in general, if this was a 3 by 3 system, you have no choice but to put this into some algebra system and to see what size this is less than here. So this trick now only applies for 2 by 2 systems. Okay. And let me explain. Because we're right now stuck at determining our stability properties because we don't know the signs of these items. So this trick is called, it's not a trick, it's a theory, but I call it a trick because it only works in 2 dimensions. It's called the trace determinant plane. So in 2 by 2 systems, when you have multiple parameters like this, and you do not want to analyze or even compute these eigenvalues. Yes? Plane. It should say plane. And even computing these eigenvalues is very difficult because you have to solve the characteristic polynomial too. So you don't want to do this. So let me go back to our simple case. Supposing I just have some matrix A with entries A, B, C, and D. In general, the eigenvalues of this are given by what? They're given by the characteristic polynomial, which is lambda squared minus A plus D lambda plus AD minus BC dx. So that's the after some simplification. But in general, this is the characteristic polynomial that will determine the eigenvalues of this matrix. But notice that we have 2 very special terms in here. What is this term? If you look at this matrix, what is A plus D? What is that? Trace. Okay, so this is the trace of it. And what is AD minus BC? Determinant. Interesting. So in other words, the eigenvalues are a function of the trace of the matrix and its determinant. Let's see what that tells us.
Only for
Only for 2 by 2. Because in 3 by 3 you'll have extra cofactors and the formula doesn't make any sense. Okay, so we've established that there's a trace and a determinant. So let me then write it in terms of that. So lambda minus trace A lambda plus determinant A is equal to 0. And now I can solve for lambda because it's just a quadratic equation. So this implies that lambda, I'll call it 1 and 2, is equal to 1 half trace A plus or minus square root of trace A squared minus 4 times determinant A. So those are the eigenvalues for any 2 by 2 matrix. Okay. And in particular, we have interesting properties. Namely that if I add lambda 1 plus lambda 2, I get trace of A, as you can confirm. And if I multiply lambda 1 times lambda 2, I get the determinant. So the sum of the eigenvalues is the trace. The multiplication of the eigenvalues is the determinant. Okay. So now out of sheer laziness, because I don't want to write TR and DET every time, I will denote by T trace A and by D determinant A. Because I don't want to keep writing.
That the sum and the multiplication, that's also a formula from polynomials.
Yeah,
Yeah, it's the, I can't remember.
I can remember. I know.
Yeah,
Yeah, I know what you mean. Yeah, I did bring it. Okay. Now what can we say? Well, in particular, we have now a bunch of cases that we can analyze the signs of these eigenvalues purely in terms of the signs of the trace in the system. Oh. So in particular, the eigenvalues are, one possibility is that they're complex with non-zero imaginary part, which will occur if this factor goes to less than 0. In other words, if t squared minus 4d is less than 0, another possibility is that the eigenvalues are real and distinct just by looking at, as usual, the sign of the square root. So this case would be if t squared minus 4d is greater than 0. And of course, the third case is your favorite case, where it's real and repeated roots. And this will be, of course, when t squared minus 4d is equal to 0. And that's why we call it the trace determinant plane, because the entire geometry of this 2 by 2 system is determined by Td. So if you were to sketch d and t and the different values, you get a parabola. So depending on which side of the parabola you are on the plane, that's the sign of the eigenvalue. So this saves you from having to compute eigenvalues. And you can just look at the signs of the eigenvalues just by looking at the trace of the Jacobian and the determinant of the Jacobian. But there's more we can say about this actually. That will be even more helpful to you. Okay. In particular, so breaking this down further, we have some subcases of these. So let me take the first subcase, which is if it's less than 0. So if t squared minus 4d is less than 0, the real part of this is going to be t over 2. The real part of my eigenvalue will be, of course, just a half t. So remember, we analyze stabilities by looking at the real parts of the eigenvalue. So to analyze stability of my Jacobian, all I need to look is the sign of t over 2, which is a trace divided by 2. So I'll show you this in an example, or our own example. So in particular, but these are still complex. So we have a sink, if t is less than 0. We have a source, if t is greater than 0, as you know by now. And a saddle, or a center I should say, because these are complex, if t is equal to 0. So that's for the general case of the complex eigenvalue. So you can see we can determine sink, source, and center behavior just by looking at the sign of the trace, which is incredibly useful. But I will not respect this to a theorem because it only works in 2 dimensions. And it gives you false hope. Many sleepless nights of false hope, actually. So, but for our purposes it's okay because everything we've been doing so far has been 2 by 2. So it's okay. Okay, the second case, which is the greater than 0. So these are when the eigenvalues are purely real. So if d is less than 0, which is the determinant, you get a saddle. And why is this? Because d is the determinant, it's lambda 1 times lambda 2. So the only way for you to be less than 0 is if 1 is negative and 1 is positive. Right? So d is equal to lambda 1 times lambda 2, and the only way this this can be less than 0 is if lambda 1, 2 are of different sizes, obviously. Okay? So that's one case. If b is less than 0, and further we have, this implies that t squared is less than t squared minus 4t. So what happens if you factor? What happens? What are the implications of this inequality? So t squared less than t squared minus 4d. This implies that plus or minus t is less than the square root of t squared minus 4. Just by square root equals. Okay. So in particular, we have t plus square root of t squared minus 4d, which is greater than 0. Or we have that t minus square root of t squared minus 4d is less than 0. So now we can say, based on this, that if the determinant is positive and the trace is negative, then both of these are less than 0. T plus and minus are less than 0. So if both are less than 0, lambda 1 plus lambda 2 is less than 0. That means you have a sink. So this implies that you have a sink if t is less than 0 and b is greater. Because both lambda 1 and lambda 2 are minus, so the determinant would be positive and the trace would be negative. And you have a source if the opposite is true. If t is greater than 0 and d is greater. So this will help us tremendously now determine the stability and actually finish this boring disease modeling problem. Okay. So I think I've erased the Jacobian, yeah, oops. But you know it, I've written it down. And now I've So now, if I want to determine the stability properties at this point too, I can just apply this trace determinant stuff to my Jacobian. Okay. So, if you go back to that Jacobian matrix I wrote down, evaluate it at this second point here, you will see that the trace is equal to minus mu plus beta tau divided by b plus mu. And this will always be less than 0 if that assumption I wrote down before, that the population must be positive. If beta is greater than 0. And of course, we also are assuming that b mu is greater than 0. So our trace is always negative, no matter what. So this implies that both of my eigenvalues are negative, or less than 0. So in fact, this point number 2 is what then? Sink, very good. Point 2 is a sink. But now, go back 2 classes ago, I think. If both eigenvalues, and there's only 2 eigenvalues of this system, both of them are negative, what else can we say about this system? In addition to that, it's a sink. What else can I say? asymptotically stable. Ready? And what is that theorem called? Okay, okay. It's the outcome.
Yeah.
Wow.
Said at the same time.
He said it's the theorem of asymptotic stability. That was Jared's answer. It's very generous. I'm sure there are some American textbooks that follow that. Yes. So, not only is it a local sink, but also by Lyapunov's stability theorem, point 2 is also asymptotically stable. This means that all of the orbits in a neighborhood of point 2, as time goes to infinity, over a long time, will approach this point, will converge to this point. That is the difference between stable and asymptotically stable. Question?
What is the P2?
P2 is point 2. I didn't want to. Equilibrium function. Equilibrium. Question.
So, I don't know when this was, but a few lectures ago, you said how if you, let's say you have a set, and then you apply the flow operator to it, and if it does not leave that set, then it's called something.
Invariant.
Invariant. So in this case, because, let's say a small region around the sink, would that be the invariant?
Yes, because the equilibrium point itself is an invariant.
Okay.
Yes. So any orbit will be trapped. Yes. But so it's asymptotically stable. And it's a sink. So this means that, well, let me write it. So this is a very special state of the system, because over time, all of the states will approach this if you set beta to have this value to begin with. So this is a point I wanted to make that is often missed in dynamical systems. The parameter choices are your choices. Either you determine them from data, so you hire some stats guy to do regressions for you, and then they figure out what these coefficients are supposed to be. And then you put them in your system, you see what happens. But often, there's no justification for why people pick the values they do. And this is true in physics, in cosmology in particular. Because, I guess an example way to think of this is, and this is an example I like a lot. If you have a ball, let's say, on top of some hill, and you roll it, the dynamics of this ball is completely determined by Newton's laws of motion, right? Okay. So you know that. Once the ball starts moving, it's completely deterministic by laws of physics. But what is not determined by the physics or the equations is where you start the roll from, the so-called initial condition, or the initial parameters. So this is often missed in many classes, many courses. So this is, in some sense, your choice. Once you set up the problem, then physics takes over. But the problem is that what is the justification for it? So in biology it makes sense, in some sense, because you have data of diseases and how fast they spread and things like this that allow you to determine these parameters up to a certain degree of accuracy. Because that's also a statistic. But this is often missed. So that's why you have to study things like bifurcations and things like this, which I will do. Question?
So by initial condition, you refer to a set of exogenous variables?
Yeah. Exactly. And economists are famous for doing this, actually. Have no justification whatsoever for the values of parameters they choose. But I will control my. They don't want to get much trouble. In fact, I think I burned every bridge with every non-math in this university. Yeah. I can't help it.
One day you're going to go to the doctor, and they're going to see one of your lectures, and you're like, oh, you said biology was useless, right?
My sister is a biologist. You can imagine the dynamics in our home. She thinks physics is stupid, and I think biology is stupid.
Are the dynamics dynamic?
It's a game theory. It's a prisoner's dilemma inside my house.
So it's not a simple.
She's younger, so she tends to be the same, and I'm the source. Okay, anyway. So I just wanted to make that clear. So, like we did for the SIR case, we can analyze bifurcation. The stability properties of the system will change based on the value changes. So let's see what happens. So, as usual, if you forgot already, this means we analyze the linearized system about some equilibrium. In particular, as we did for the SIR case, where the linearized system is zero. And this tells you destabilization. Okay, so at the first equilibrium point, which was tau 0, the linearized system, so doing exactly the same steps I did for the SIR model, the linearized system becomes what? It becomes S prime is equal to minus mu s plus minus tau beta minus mu times I, and the I prime linearized equation at this point is minus v plus tau beta. So now we just look where these become zero. So remember our language, how we talk about these things. We say the following. We see that S destabilizes this equilibrium point. What happens when mu is equal to tau, which is equal to 0? That's one possibility. Further, now we look at the I prime equation. We see that I destabilizes this equilibrium point when minus v plus tau beta is equal to 0. Or, if you solve this equation or rewrite it, it means that when tau is equal to v over beta. So there's that cascade v over beta factor. And now I will give you a name for it, finally. Tau represents the total population. Remember this? That's what I call tau. Yes? I cannot continue if you do not recall this. It won't make any sense what I say now. So the total population bifurcates when v over beta is equal to tau. So what is this v over beta called? It's called the threshold population. I think that's how you spell it. Threshold level, threshold population. So there's something critical about when the population hits v over beta in your model. Something will happen when the population is less than v over beta, something will happen when it's equal to v over beta, and something will happen when it's greater than v over beta. That's what you mean by bifurcation. So in detail, what happens? So that's for the first equilibrium point. Now if you do the bifurcations of the second equilibrium. Yes?
What's the numerator of that?
It should be V with some weird French accent here. I don't know what happened. It's V. Like, I don't know, I drew a circumflex over the Okay. That's for the first equilibrium point. We also have to analyze the linearized system about the second equilibrium point. Namely, when S star I star is equal to V over beta, mu tau minus V over beta. V plus V. Okay? And once again, you just look at the Jacobian and write out the linearized system. So the linearized system is given as follows. S prime is equal to minus mu. So I'm just doing a clean substitution here, nothing complicated. Times S plus V minus mu minus V minus mu. And then you have the I prime equation. So you just read this directly off the Jacobian. It's nothing complicated. You get mu minus V plus V tau over V plus mu. And now we do the same thing again. We see where S prime and I prime is equal to 0. And it will not be surprising, our answer. So, the I equation is obviously easier to read off when that goes to 0, because it's just when the numerator goes to 0. So, I destabilizes this point when tau is equal to V over beta, once again. So it shows up in both equilibrium. So in other words, what we have is a bifurcation line at tau is equal to V over beta. If you were to plot this in some parameter space, you see there's a line, V over beta. So, if tau is greater than V over beta, what you can conclude is that this point, as you know now, is a sigma. Because we just did the stability analysis. And this was the condition for point 2 to be a sigma. In fact, it's asymptotically stable. So you have some transition then that's taking place. Because it's never a source, right? We proved that. It's only a saddle or it's a sigma. I mean, point 1 is a saddle. So we have a transition from when t or tau is equal to V over beta, and then when it goes to greater than V over beta. And you see the stability changes as we change this value. And in fact, in other words, for tau being greater than V over beta, our first point, equilibrium point 1, was found to be what type of equilibrium point? The first equilibrium point, the tau 0 point. What was it? What were the signs of its eigenvalues? Was it a sink? Was it a source? No, S star I, when it's tau 0, what was it? Saddle. I did write saddle, right? No, I wrote saddle. Asta wrote it. You have it, saddle? Yeah.
It's our gold standard.
You wrote it down. Okay, good. So, for point 1, when tau is greater than V over beta, we see that point 1 becomes a saddle. Okay. And for tau greater than V over beta, what does point 2 become? What is point 2? What type of point is point 2? Always C. Right? Yes? Do you recall this? So, when tau is greater than V over beta, we have two equilibrium points. One is the saddle, one is the sink. But they both exist simultaneously in our space, SI space, for this value of tau. One is the saddle, one is the sink. So what else can we say then, the final conclusion about this dynamical system that connects two distinct equilibrium points? What do we call that, do you remember? Very good. So in fact, with this choice, when tau goes to V over beta, we have a heterophilic orbit that forms in our system.
Shouldn't there be one more point then?
Why?
Because if you said there's a saddle.
Sequence.
there's a sink.
That's a sequence. Heterophilic sequence is when you start with source, saddle, and then sink. But a heterophilic orbit is just an orbit that connects two distinct equilibrium.
But I'm saying for this system, you have sink and a saddle, right?
Yes.
So then, isn't the saddle consequence of having the source and the sink?
No, that's, a lot of people are confused about this for some reason. A saddle is when the eigenvalues are different signs. That's its characterization. A source is when all of the eigenvalues are positive, and a sink is when all of the eigenvalues are negative.
So, okay, so let's say we're talking about like a multi-dimensional kind of case. So let's say you had some plane that's curved like this.
Yes.
And then it would be like this.
Yes.
That would be a saddle point, right? The connection of the.
Yes.
Right?
Yes.
So then, wouldn't that mean that one of the curves could be considered a source because it's pushing outwards and the other one's coming in?
Be careful. You have to look at the dimension of the unstable, stable manifold. So don't get confused. A saddle, by definition, in any dimension, has some orbits that live in the stable manifold and some that live in the unstable manifold. But that's not the same as having a source or a sink. Because a source has all of the orbits that live in the unstable manifold. A sink has all of the orbits living in the stable manifold. A saddle has a combination of it. So don't get confused by this. But anyways, we have two distinct equilibrium points with two vastly different behaviors, and we call it a heterophilic orbit. So that's what happens at this bifurcation. And that's what it is. And I'll show you the diagram. And it connects P1 to P2. And what can we say about this in terms of biological application? So we have no homophilic orbits because we don't have any points that connect to themselves. We do not have that complicated a system. But in conclusion, what we can say is that biologically, this disease, what we are modeling, is established. That's a good word. In this population, when the total population exceeds the threshold level.
Does that mean you can't get rid of it?
Right. You can't eradicate. Interesting. Well, maybe that's a fault of our model, but a fault of the biologists. So let me show you finally this diagram. Keep downloading it, never have time to show you. What is lumen here? So what I did was I simulated this dynamical system very simply, and I'll give you the parameters I use. So these are completely junk parameters. They have no physical relevance, but you're reading my emails as well. I suppose so. Just a lot of fights with a lot of people. So this numerical simulation, I used beta is equal to 1, v is equal to 1, mu is equal to 1, and tau is equal to 2. They don't mean anything, they're just for numerical illustration. And what you get is you have the two equilibrium points. So, which do you think is point 1 and which do you think is point 2?
The middle one is point, 2.
And why is the middle one point 2? And which then is point 1? And you can see the saddle behavior of point 1. Because you have a bunch of orbits that approach it, but then they're repelled by it. You have a bunch of orbits that approach it, they're repelled by it. And over time, all of the orbits go to point 2. So it's asymptotically stable. So this is what's happening in this system. So you start with your population that has no disease, right? Point 1 is not necessary equal to 0. And eventually, all of the population goes towards the exceeding the threshold.
That's what it's called.
Exactly. Every single orbit approaches that point. No, it does get there. It converges to it. So that is the difference between a center and a sink. A sink has convergence to that point. A center just keeps orbiting around it, but never hits it. Asymptotic, so in dynamical systems, asymptotic means as time goes to infinity. So in that asymptotic sense, every orbit will converge to that point. But over a very long time.
So you said it was heteroclitic, right?
Yeah, so you see all of these orbits that are joining. Maybe it's poorly drawn, but all of these orbits are joining point 1 to point 2. There's a bunch that do. There's supposed to be a lot more, but Mathematica cut off this space. I don't know.
Heteroclitic doesn't mean that, okay, it just means, there's no like other direction that goes back to the other one?
That's a homoclinic. So heteroclinic means I have some point here, I have some point here, and they're connected by some curve. That's
But I mean, like, you know how in like graph, you have a directed graph? So like this one, you said everything is going towards the center?
yes.
So homoclinic doesn't necessarily mean there's something coming back, like an old
Homo does, not hetero.
heteroclinic doesn't mean, it just means there's some kind of connection.
Exactly. Some connection in their phase space that connects point 1 to point 2. This is hetero because it's too distinct. If it was like this, then it would be a homoclinic.
Oh, okay.
So our circles that we had for the rock, paper, scissors, those are a series of homoclinics. If you start at, if your equilibrium point lies along the orbit, but in that case it will not. So it centers along. No, they are not. It's actually exponential. Yes.
So asymptotically stable means it will never be centered.
Say it again.
Asymptotically stable means it will never.
It will converge. So you see, it's converging to point 2. All of the orbits are converging to that point. So it's asymptotically stable.
So if you were to describe the behavior of the global system, you would say it's synced?
For global, you say, in fact, that this is an attractor. Point 2 is an attractor. We didn't do too much global because I don't want you not to worry about finding limit sets. Only if you want to do it, we can do it. No, but it's much harder to prove global because you have to use the Lassalle's invariance principle. What I wrote down. Yes. This one you want, because one is definitely a cell. So your global future attractor will always be in terms of the same. Any questions about this? Yes?
There wouldn't be no equilibrium point on the left of that top, not some point.
Why?
Because all the points are going on one on the side.
Um,
It's ridiculous very small point.
Yes, so this is a good question. Remember, I reduced my system from 3 dimensions to 2 dimensions. So there's an entire axis I'm missing here. But you can easily get it because you can write down what the outcome is. So that is the disadvantage of reducing the dimensional system. You get some missing information, but you can always get it. But the dynamics are entirely described. Any questions about it? Okay, so see you all.
Everything comes.